Hello everyone, in this module we are going to learn projection formula, that is how to two-dimensionally represent the molecule with the information of its stereochemistry and some terminology that is quite often used in stereochemistry. Okay, let us discuss now about the three-dimensional representation of chiral molecules. There are different projection formulae those help us to view the molecules three-dimensionally, although it is written in two-dimensional paper. So the representation helps us to understand its stereochemistry. As discussed earlier, one such formula is wedge formula. It is also called as flying wedge projection. It is the most widely used three-dimensional representation of a molecule on a two-dimensional surface, that is paper. So this kind of representation is usually done for the molecule containing chiral center. In this type, three types of lines are used. See the given example. When four different groups are attached, the molecule is chiral. So wedge formula is used to represent it. How? Here there are three kinds of lines are used. One is this solid wedge bond, and another one is dashed bond, and other two lines ordinary lines. So a wedge and this thick line, so that represents the bond. Here bromine is attached, bromine is connected by the wedge bond. It represents bond projection that is coming towards us or above the plane of the paper. A dashed wedge line. So here iodine is connected like that. So this represents the bond projection that goes away from us or it goes below the plane of the paper. The ordinary lines, here chlorine and hydrogen are connected by ordinary lines. These lines denote the atoms, they are in same plane. So this is how wedge projection formula is represented. This projection formula is most commonly used to represent the right orientation of the atoms or groups. So the next one is Fischer Projection formula. In 1891, Emil Fischer devised a method by which three-dimensional objects can be represented by two-dimensional papers. Fischer projection provides an easy way to draw a three-dimensional molecule on two-dimensional paper, and all the bonds are drawn as solid line, this ordinary line, around the asymmetric carbon atom. Here we have two lines, one is horizontal lines and another one is vertical line. Horizons and vertical lines are used to represent the bonds, and the intersection of a horizontal and vertical line represents the central carbon atom. Isomers of different sugars in organic chemistry are the most common representation of Fischer projection. So there are few rules has to be followed while writing the Fischer projection formula. The carbon atoms in a chain are represented on a vertical line, and the non-terminal atoms are represented by horizontal lines. The carbon atoms may not be represented by the letter itself, and the intersection of two lines will depict the carbon atom at the center. All the horizontal lines of a Fischer projection formula are projected towards the viewer, and all the vertical lines are projected away from the viewer. So like this we have to use the Fischer projection formula. So a Fischer projection formula is a convention used to depict a stereo formula in two-dimensional spaces without destroying the stereochemical information at chiral centers. To convert the stereo formula into Fischer projection formula, we can apply the following procedure. If you view the molecule from this side, the atoms in ordinary line will occupy the vertical line, and the one which comes towards us is in our right hand side now, and the group goes away from us is on our left hand side. So that is the way we have to write down in the Fischer projection formula also. Okay, the next one is Sawhorse projection. The Sawhorse projection formula indicates the arrangement of all the atoms or groups on two adjacent carbon atoms. The bonds between the two carbon atoms are drawn diagonally and of relatively greater length for the sake of clarity. The lower left hand carbon is taken as the front carbon or towards us, and the upper right hand carbon as the back carbon or away from us. Here in the Fischer projection, whatever atoms or groups lying in the vertical line is down the plane. That should be written in the eclipsed form. Then we have to give the rest of the atoms in the horizontal line as such. in the same side as in Fischer projection. Similarly, in Newman projection, it is represented as given here. In these formula, the molecule is viewed from the front side along the axis of carbon-carbon bond. The carbon nearer to the eye is represented by a point and the carbon atom towards the rad by circle. The three atoms or groups on the carbon atom are shown as being bonded to dot or circle by an angle of 120 degree to each other. In Newman formula, all parallel bonds are eclipsed and all anti-parallel or opposite bonds are staggered. Hence, when we see the Newman projection, the arrangement of atoms or groups is almost the same like Sawhorse. Like this, we can also convert the molecule to wedge formula or Fischer projection formula or Newman projection formula or Sawhorse projection formula. So, this will be helping us to view the molecule without losing its stereochemical information. Okay. So, in the previous video, we learned that stereogenic center is not always tetrahedral carbon, and also we learned that all chiral centers are stereo centers, but all stereo centers are not chiral centers. Remember the stereoisomers of tartaric acid. So you can see here the tartaric acid molecule and its non-superimposable mirror image. Both are called as enantiomers. These two enantiomeric forms, which differ only in the arrangement of bonded atoms around the chiral carbon. The physical properties like molecular formula, molecular weight, melting point and boiling point and density, etc. of both the isomers are same. But if one isomer rotates the plane polarized light towards right and the other one will be rotating the plane polarized light towards left. So that is the only difference. And the third one is mesoisomer. So the mesoisomer is achiral. So we have just ignored it. So these two are called as enantiomers. So the object and its mirror image, if they are non-superimposable, then they are called as enantiomers. So think of to write down the possible stereoisomers of monosaccharides with the molecular formula C6H12O6. So there are 4 chiral centers. So you can expect 16 isomers for this. So this will be quite useful to understand the concept of enantiomers, diastereomers, anomers and epimers. Optically active chiral compounds that are non-superimposable mirror image of each other are called as enantiomers. Enantiomers always exist in pair. Hence, D-glucose and L-glucose are enantiomers. Enantiomers are the molecules which is non-superimposable to their mirror images. Enantiomers have same physical properties like boiling point, melting point, solubility, density, viscosity, refractive index, etc. Chemical properties in achiral environment that will also be same. Each enantiomers have opposite behavior with respect to the plane polarized light, and also the chemical reactivity will be different in chiral environment. Sometimes the pair of isomers are called as diastereomers. Diastereomers are those stereoisomers that are not having mirror image relationship. In other words, diastereomers are stereoisomers that are not enantiomers. They will not have mirror image relationship at all. Diastereomers are non-enantiomeric stereoisomers with 2 or more stereocenters. The pair of stereoisomer that differs in the arrangement of atoms or groups bonded with at least one stereocenter is called as diastereomers. Cis and trans 2-butene are non-mirror image stereoisomers of each other. Hence, they are also called as diastereomers. All cis-trans isomers are diastereomers. All geometrical isomers are diastereomers. All the stereoisomers except enantiomers are diastereomers. So, in the monosaccharides, glucose and mannose, glucose and galactose are diastereomers. Diastereomers have different physical properties like boiling point, melting point, density, solubility, viscosity, refractive index, etc. Diastereomers have different chemical properties like rates of reactions, reactivity even in achiral and chiral reaction medium. This difference in physical and chemical properties of diastereomers is very useful in separation of stereoisomers from their mixture. There are other 2 terms used in carbohydrate chemistry. They are anomers and epimers. Anomers. What are anomers? A pair of near identical stereoisomers or diastereomers that differ at only the anomeric carbon. that is the carbon bearing the aldehyde or ketone functional group in the sugar open chain. However, in order for anomers to exist, the sugar must be in cyclic form. Since in open form, the anomeric carbon is planar and thus achiral. As is typical for stereoisomeric compounds, different anomers have different physical properties, melting points and specific rotations, etc. So for example, alpha D-glucose and beta D-glucose are anomers. So in cyclic form, one is having OH on the right side and another one is having OH on left side. So the optical rotation will be different for both the isomers. So alpha D-glucose and beta D-glucose. Similarly, alpha D-mannose and beta D-mannose are anomers. Epimers. A pair of near identical stereoisomers or diastereomers that differ only at any one of the chiral carbon. That is, in the example as we have discussed, glucose and galactose. Glucose and mannose are epimers. So with these details, I will wind up the session. We will meet again in the next video. Thank you all for your attention.